tutorial time. So if you are if you have any questions about the midterm exam, you can let me know for now, or you can contact me later. I will provide an official midterm review probably on this Thursday after I finish all the contents about the Asphalt technology. Basically, for the midterm, we will cover all the topics from the start of this class to the lectures about the Asphalt technology. Do you have any questions about it, or do you want to know more details about the exam, or some general information about the exam? But anyway, I will have a detailed review about exam on this Thursday. If you have any questions, you can raise your hand and just ask the question. Okay. So let me go through the other computer. Okay. So if we don't have any questions, I will just continue our lecture from last week, and we will try to finish this topic, and with that we can have more time to review for the midterm exam. Okay, so last time we have some introductions about the Asphalt technologies, and we introduced the some fundamental traditional methods, the Marshall's mixed design and the Vim mixed design, and we claim their advantages and disadvantages. After that, we have some introductions about the SUPERPAVE technology, which is one of the modern Asphalt technology that we're going to use for the pavement design. So for the SUPERPAVE mixed design, it has four steps, including the material selection, the design of the aggregate structures, the design of the binder contents, and also the test for the moisture sensitivity. We started with the material selection. In the last lecture, we introduced the selections about the asphalt binder by using the weather conditions, the climate information to determine the grade of the asphalt content or the asphalt binder we have to use for the pavement design. Actually, for the SUPERPAVE mixed samples. So with the sharp definition, we will have the performance grade for each asphalt binder, including the average 7-day maximum pavement temperature and the minimum pavement temperature in the design area. We also show the definitions about these two values in the performance grade, and we showed how to find out the values about the performance grade under different reliability. Usually for the low reliability, the performance grade will cover smaller ranges of the temperature, but for the higher reliability, you need to have the better performance of the asphalt binder. For this example, you can see that the 98% reliability will be PG64 minus 34, compared with the 50% reliability, which will only cover the range of 58 to 28. Also, you have to remember that for the performance grade, we will always always choose the materials based on temperature at every 6-degree intervals. And this is actually the standard defined by the SHARP program. So that's the performance grade that we're going to define, and with that we have the some information about the properties of the asphalt binder and the different performance grade. For example, if you have the PG, if you have the asphalt binder of PG 52 and 52 minus, say that's minus 40, it indicates that the 7-day average 7-day maximum temperature is less than 52, and the minimum pavement temperature is higher than minus 40. And you can find out the properties of this asphalt binder, like the flash point temperature, 230 for all type of the asphalt binders. And you also can find out the viscosities, the dynamic shear, the mass loss, and so on. Those information, those would be the features of the asphalt binder that we have considered in the pavement design. But we will not go through those details. This would be some technical features of the asphalt binder. So the other thing we have to consider about the performance grade of the asphalt binder is the traffic conditions on the road. Basically, the grade selection is highly related to the speed of the trucks, the vehicles, especially trucks moving on the road. If the vehicles or the trucks is moving slowly on the road, then you have to choose a higher performance grade. If it's moving faster, usually you can choose something someone with smaller performance. For example, if we consider the toll road, usually the vehicles moving on the toll road will have a very high speed. Say that if the speed of the truck is around 90 km/h or even higher, then we can choose the performance grade of 64 minus 22. This is just one example. But for the same pavement in that area, if the trucks are moving slow, for example, if there's a toll booth, the trucks are moving very slow, then we have to increase the average 7-day maximum speed, maximum temperature from 64 to the next grade, that is about 70 degrees. We will still keep the minimum temperature. But if we go to the wait station where all the trucks have to stop there, then we have to further increase the performance grade. Like for the same condition, the same road, at the wait station, the performance grade should be changed to PG 76 to 22. This is for the stopping scenario. So basically, with a low speed traveling on the road, we need to have the higher performance of the asphalt binder. And this would be the criteria that we're going to use to decide the performance binder, in addition to the temperature or the climate conditions that we have to use for the selection. Basically, if we are considering the standing situation where the speed is less than 20 km/h, or also we need to think about the volumes of the traffic on the road. For example, for 20 years designed life, the ESAL, they estimated equivalent standard axle load, which means that represents how many volumes over 20 years on the pavement, on the designed pavement. If the designed ESAL is less than 0.3, then you don't need to do any modification. So the performance grade will be the same for all different speeds. But if the volume is between 0.3 and 3 million, then we have to make some changes. For the standing situation, we need to increase. We need to have 2-degree increase, which means that we have to increase the average 7-day maximum speed about twice of the interval. The interval is set as 6 degrees, and this two indicates that you need to increase the maximum speed, maximum temperature about 12 degrees. And if it's road with slow traffic, then you just need to increase that one for one interval. That is 1 times 6, which is 6 degrees. If it's a standard road with a speed higher than 70 km per hour, then you don't need to make any modification. And this actually applies for two different levels of the traffic. But for the road with very heavy traffic, like the 20-year design ESAR is higher than 30 million, then we also need to do some modification about the performance grid. Even at a standard speed, even when the speed is higher than 70 km per hour, we still need to increase the degree of the average 7-day maximum temperature around 6 degrees. So that is times 6. So this is the way for you to choose the performance grade. You have to select the performance grade based on the climate condition and also based on traffic condition. For the traffic, you need to think about the volumes and also the speed moving on the road. So with that, we have the information about the performance grade selection, and this one is actually defined in the Asphalt MP299 protocol. So you can try to check more details by searching Asphalt 299 online. And the next thing we have to consider about the material selection is the aggregates. We need to carefully choose the aggregates based on their gradations for the hot mix, the asphalt. For the selections of the HMA aggregates, we have to consider the maximum size and gradations, the cleanliness, the toughness, the particle shape, the surface textures, absorptive capacity, affinity for the asphalt contents, and the frictional properties for the surface cores. So all these features will be highly related to the frictions of the aggregates, asphalt aggregates, and also determine the shear strength of the asphalt pavement. In this lecture, I will just show you the most critical features that you need to consider for the material selection. Usually for the SUPERPAVE mix design, we will consider 5 different types of the materials or the aggregates. That will be number 1, stone, 12.5 millimeter chips, 9.5 millimeter chips, the manufacturer sand, and the screen sand. I will give you more details about the properties of these 4 types of the aggregates in the future, including their grain size distributions and how to mix them to find out the appropriate sample and do the test. So for the aggregate properties, we have in the selections of the aggregate, we have to consider 4 properties, 4 most critical properties. The first one is called the coarse aggregate angularity, which will shows the shape of the surface for the aggregates. And the second one is called the fine aggregate angularity. This one will only focus on the surface and the shape of the fine particles in the material. And the third one is the flat and elongated particles. We want to see whether the shape of the particles is long or is flat. And the last one is the clay content, which we want to find out the sand equivalent value to determine the fine particles in the aggregates. So I will go through each features one by one and also let you know the test will be applied to measure those properties. And we have the criterions for each property for you to choose the appropriate aggregates. So first, for the coarse aggregate angularity, which is also abbreviated as CAA, usually we will have 2 tests to identify the the features of CAA. The first one is called the Asphalt TP61. With this one, you can identify the number of the faces for the aggregates with the angles. For example, in this figure, you will see two different aggregates. The one on the left has the 100% angular face, which means that this aggregate is very sharp. It has very sharp corners. But for the one on the right, it does not have all angular faces. Instead, it has some non-angular faces. With that, you can see that the surface of the aggregates is much smaller compared with the one on the left. So this is the one. This is the one we get from the Asphalt TP61 test, and the one on the right shows which is the Asphalt TP56 test. It will try to identify the void contents for the aggregates, and basically, if the void contents is higher, this will all usually related to the angular faces of the aggregates. With the angular or irregular surface of the aggregates, there will be more space of the amount between the aggregates, and with that, there will be a higher air voids for the aggregates. And in that sense, the CAA, the coarse aggregate angularity, will be larger. So these two will be equivalent to each other. The test will find out the void contents, and based on the value of the void contents, you can have some ideas about what's the value of the what's the level of the coarse aggregate angularity. So this is for the coarse materials, and we actually have the criterions for you to select the aggregates with respect to the for the design of the SUPERPAVE. For all the 5 different materials that we selected in the previous slides, the first 3, number 1 stone, 12.5 millimeter chips and 9.5 millimeter chips, are the coarse aggregate. And if the particles has more than one fracture faces, then we will have several criterions for them. For example, for the number 1 stone, usually you will have the aggregates with 92% of the aggregates with more than one fracture faces. And for the 12.5 millimeter chips, it usually has 97% of more than one fracture faces. But for the selections, we have to make sure that if this 12.5 millimeter chips has a minimum of 95% particles with 1 plus fracture faces. If it's less than 95%, then it's not an appropriate materials for the SUPERPAVE mix design. For 9.5 millimeter chips, the minimum value would be 95%. It's still 95%. But usually for most of the nature materials we get from reality, the value of the percentage of the particles with more than one fracture faces will be around 99%. The selections for the particles with more than 2 fracture faces will be different. Usually for number 1 stone, this kind of percentage is 88. For 12.5 millimeter chips, that is 94%. And for the selection, we have to make sure that there should have the minimum value of 90%. So that's for the coarse aggregates. We also need to check the fine aggregates that we're going to use for the SUPERPAVE mix design. Usually the fine aggregate angularity should be estimated based on a test which is called the uncompacted void test. This one it's the FAA is usually defined as the percentage of the air voids presented in loosely compacted aggregates smaller than 2.36 millimeters, which would be the fine particles. With the fine aggregate angularity, we are able to maintain a very high degree of the internal frictions, and with the high internal frictions, we are able to resist to the rotting for the pavement structure. So the FAA is very important for the aggregates that we're going to use for the SUPERPAVE mix design. Usually the FAA can be measured through the Asphalt test 304, and the also this test result will be affected by the particle shape, the surface texture, and the grading information. And the FAA test will be usually be applied with the figure on the left will shows the instrument applied for the FAA uncompacted void test, and usually you're gonna put the sample, the sample, the fine aggregate sample in one furnace, and then they will collect the sample at the cylinder below, and we can estimate the uncompacted voids with this equation. In this equation, V would be the volume of the cylinder. So this is the volume of the cylinder, and the W here is the sample mass. And also GSB, it's the dry box specific gravity. You can actually find out the detailed definitions about GSB and some other variables that we're going to use in the next few lectures from the tutorial 3. There will be very detailed definitions about those variables, and especially the variables related to the SUPERPAVE mix design. And of course, this uncompacted void test is applied for the fine aggregates, which will be used for the manufactured sand and screen sand. There will be some criteria about the percentage of the air voids from the test. For the manufactured sand, we want the percentage of the air voids to be at least higher than 45%. Usually, the typical value for the manufactured sand is 52%. For the screen sand, we do not have any requirement, but the typical value is around 40%. So that is for the fine aggregate angularity. The third one is the flat or the elongated particles. We want to measure the flat and elongated particles through the experiment. And this one is actually conducted by the ASTM test D4791. Again, if you want to know the details about this test, you can just search this keyword to find out the procedures of the measurement. So with that, we can find out the percentage of the fine and elongated particles in the aggregates. Usually, this one applies for the coarse aggregate, because we only care about the shape of the coarse aggregate instead of the fine particles. So for the number one stone, actually for all these three stones, usually the percentage of the flat and elongated particles will be around 0% for the SUPERPAVE mix design, but we have some buffering percentage for the flat and elongated particles. Overall, we want to make sure that this percentage should be smaller than 10%. If it's higher than 10%, means that it's not appropriate for the SUPERPAVE. We have to either remove the flat or elongated particles, or we have to find out some other combinations from different aggregates. And the last one is the clay content. We're going to use the sand equivalent test to measure the clay contents. This one has been introduced in the previous lectures when we are talking about the properties of the soil. We have the some standard procedures to measure the sand equivalents. Usually we only measure the materials passing through number 4 sieve with the size. With the size of the particles less than 4.75 millimeters, and through the experiment we can find out the clay reading and sand reading, and then with these two readings we can calculate the sand equivalent. And usually for the sub-base, the sand equivalence is around 20. For the granule base, it's 30. For the aggregates, if the aggregates applied for the asphalt concrete, that is 45 to 50, and for the concrete sand, that is 76. For the sand equivalent test is only applied for the fine particles, so we can have some typical values for the manufactured sand and the screen sand. For the manufactured sand, the typical value is 47. For the screen sand, it's 70, and we only have the criterion for the manufactured sand, where we have to make sure that the sand equivalency is at least higher than 45. And if it's smaller than that, it means that the is not appropriate for the SUPERPAVE, and there are too much contents about the sand material, the large course of the aggregates. So with that, we can summarize all the 4 feature properties that we're going to use for the SUPERPAVE aggregate selection. Also, it's related to the designed traffic volumes applied at the pavement. Usually, we will categorize this volume into 5 levels, less than 0.3, 3 to 5, 0.3 to 3, 3 to 10, 10 to 30, and larger than 30. And this for all the 4 materials, we have to consider the pavement design. If the materials is within 100 millimeters of the sieve, we have one criterion. If it's larger than 100 millimeter, the depth is larger than 100 millimeter, then we need to go through the another criterion. For example, for the cost for the CAA, we have some minimum values. If the traffic is between 0.3 and 3, then for the CAA, if with the depth less than 100 millimeters, the percentage of the particles with more than 1 fracture faces should be higher than 70%. But there isn't any requirement for the percentage of the particles with more than 2 fracture faces. And if it's higher than, if the depth is higher than 100 millimeter, then the percentage should be 50%, and there's no requirement for the particles with more than 2 fracture faces. Similarly, for the fine for FAA, we are going to use the uncompacted void contents. If the depth is smaller than 100 millimeters, then the percentage is the minimum value is 40. If it's higher than 100 millimeters is still 40, but it will have some different values at a higher traffic volumes. For the standard equivalence, we have the minimum value of 40 for the volume, for the traffic volume of 0.3 to 3 million for the designed year. And for the flat and elongated particles, the percentage should be less than 10%. You can find out the criterion for the other level of the traffic volumes and the depth of the materials applied. Okay, so this is the selections of the aggregates for the SUPERPAVE mix design. And with that, we finished the first step of the SUPERPAVE design. Where we can know how to find out the appropriate asphalt binder, what kind of materials is appropriate for us to use for the SUPERPAVE aggregates. And do you have any questions for this first step? Okay, if we don't have any questions, I will jump to the next step about the design of the aggregate structures. We need to find out the appropriate grain size distribution for the aggregates. So let me try to open the lecture for the second part of the S4 technology. So we have already introduced the material selection, and the next thing we need to do is try to find out the appropriate structure of the aggregates for the SUPERPAVE mix design. So with that, we should first identify what's the purpose for us to design the aggregate structure. Basically, we select the appropriate aggregate structure to establish some trials, and we're gonna check the performance of the trials in the lab, and then convert this one to the field structure, and then we can know how the design will work in reality. So with the trials, we will first check the aggregate property. We will compact the specimens to represent the realistic traffic load. We're going to evaluate the performance of the trials under different conditions, traffic load, and different moisture levels. And also, by these properties, we can then select the appropriate aggregate structure which can satisfy the requirement that we have for the pavement in their design area. So first, for the aggregates, for the design aggregates, we can use the soils that could be the nature materials, or could be some processed materials, processed or sorted materials. And we can use multiple materials and mix them together to get the desired feature that is required by the pavement. In the selection of the pavement aggregate structure, we have to pay attention about the size of the particles. Usually we're going to use two variables to represent the aggregate size. The first one is called the nominal maximum aggregate size, which we will have an abbreviation of the NMAS. And this will represent the size, one size larger than the first sieve, which can retain 10% of the particles. And this one is actually comes from the sieve analysis. And the next variable for us to evaluate the aggregate size is called the maximum aggregate size, which would be the which will represent the one size larger than the nominal maximum size. So this one is not coming from the sieve analysis. Instead, once you identify the nominal maximum aggregate size, we can then go to the next level, next size, which is the next larger size, to identify the maximum aggregate size. In the design of the aggregate structure, we have to focus on the grain size distribution of the aggregates. And actually, there will be some criteria for us to choose the trials. For example, you can find out the graph. Usually, you're going to use the graph of the sieve size, which you will raise to 0.45 power. That means 10 to the power 0.5. So you have, this is not on a linear x-axis. Instead, is something converted with 10 to the power of 0.45. So in this graph, you can see a set of the square dots. So this one, the first one here, represents the 100% passing, which will be the maximum size. So it means that all the particles can passing through this size, the size here. That's the maximum size. And we also have the nominal maximum size. And we need to make sure that this size of the sieve can retain the particles less than 10%. Usually we will have the upper bound and the lower bound of this lower bound of the percentage for this size. And in addition, we can find out the maximum passing for the particles which can passing through the sieve with the size of 9.26, and also we have the up and low for the particles with the size of 2.36. You can find out the up and the low at the size of 0.075. This one will usually represent the screen sand. And this one will represent the manufactured sand. And this one will represent the 9.26 millimeter chips. And this is a 12.5 millimeter chips. And this will represent the number 1 stone, something like that. So once you have those upper and lower boundaries, you can then identify, which is also called the control point. You can then identify the grain size distribution for any aggregates which will fall in this upper and lower bound. It could be applied. It could be considered as a candidate aggregates that we're going to use for the selections of the aggregate structures. Another thing I have to mention is that usually for the design, we will have the restricted zone. This one comes from some empirical data. The grain size distribution should not passing through any part of this restricted zone. You have to design the aggregates to avoid this small area. And with that, you can, in the design, you can actually choose multiple samples. The orange line is one sample, which will satisfy all the requirements that we have for all the control points. You can also get another line as in the second sample, which could be something like this. But you have to make sure that they satisfy all these requirements. And you can get another one which will satisfy all those requirements at the critical controlling points. And once you have identified those trials, you can then use those trials to conduct the compaction test to understand the features of the SUPERPAVE mixed designed samples. Generally, the trials will come from the 5 different type of the materials that we defined previously. Generally, for the first one, this one will represent the number 1 stone. And for the second one, that is the 12.5 millimeter 12.5 millimeter chips. And for the last one, for the third one, that is the 9.5 millimeter chips. And this one is the manufactured sand, and last one is the screen sand. You will try to do the mixed all these 5 samples to create different trials, and all these 3 trials should satisfy the gradation requirement in the previous page. So that's the first step, and you can actually try to find out the grain size distribution of the 3 trials. They will actually all satisfy the requirement as we defined in the previous pages. And this is actually the percentage of the 5 different materials that we're going to use for these 3 trials. We have trial blend 1 with the number 1 stone of 25%. The 1/2 millimeter chips 15%. 3/8 chips of 22%, manufactured sand 18%, and screen sand of 20%. You can have the other combinations for the second one, 30, 25, 13, 17, and 15, and also have the trials 3 with different combinations. So with that, you can then try to measure, as what we do in the previous lecture, we can measure the aggregate properties, including the coarse aggregate angularity, the fine aggregate angularity, the percentage of the flat and elongated particles, the sand equivalency, the combined GSB and combined SA. So these 2 values, GSB represent the effective gravity of the binder, and GSA will represent the apparent specific gravity of the aggregates. You can actually find out the definition of this. The definition of these 2 variables from the tutorial on tutorial 3. So I will not go through the definition again. So you can go back to check the tutorial 3 to see how these 2 variables are defined. Usually for the SUPERPAVE mixed design, we have the requirement about the some criteria we're going to use for those 5 properties, or 6 properties. For the coarse aggregate angularity, we want to have the minimum value for the minimum percentage of the particles with more than 1 fracture phase, and as 95% for the more than 2 fracture phase, 90%. For the trial 1, you can see that they all satisfy the requirement. Is 96 and 92%. Trial 2, 95 and 92%. Trial 3, 97 and 93%. They all satisfied. And for the FAA, the minimum value is 45. What we observe that they are all larger than 45. And for the percentage of the flat and elongated particles, they are all 0%. It's also satisfied. For the sand equivalency, all higher than 45%. So this indicates that all these 3 trial blends will satisfy the requirement of the aggregate properties. And if the conditions are not satisfied, you need to go back to the selections of the trial. Try to use a different percentage of each of these five materials and try to make sure that they satisfy those requirements. And then the next thing we have to do is conducting the compaction. So we are going to use the gyratory compaction test, and this kind of compaction will be used for us to get the sample, try to put the mix the asphalt binders and aggregates together. Actually, this is a separate topic about the second step of the aggregate structure design. I would like to keep this one for the next lecture, and this one is highly related to the lab 3 experiment. If you have time to visit the lab this Wednesday, you will have ideas about how the compaction is conducted, and then we can come back to check what's the features of the gyratory compaction test and why we have to do those experiments and what kind of variables we're going to need to measure from the test. With that, I will try to stop the lecture here today, and let's see whether you have any questions. So, do you have any questions about the about this lecture? Or do you have any concerns about the experiment and the also the exams? Again, as I said, that I will have more details to review for the format. The contents will be covered in the midterm exam on this Thursday. Okay. If we don't have any questions, I guess that will be the lecture today. And thank you very much for your attendance. I really appreciate your work in this class. And just feel free to send me email if you have any questions, concerns. And also, I will have an office hour this Thursday at noon time. If you have any questions about the exams, feel free to drop in the channel, the exam channel, the office hour channel in Teams. Okay. I think that will be all today. Thank you very much for your time. And with that, I will close the meeting today. And hopefully we'll have a good week, and I will see you on Wednesday.